It's my pleasure and honor to introduce you to the MITRE Corporation's Early Career Research Program. For the past 3 years, MITRE has invested $1 million each year to develop science, technology, engineering, and mathematics leadership. Created within MITRE's Innovation Program, the Early Career Research Program helps develop critical leadership skills, including how to perform research, how to manage a research project, and how to communicate results effectively. The Early Career Research Program is highly selective, and each participant pursues a particular research challenge under the careful guidance of an experienced research mentor, often simultaneously pursuing an advanced degree. Many participants work half-time on the direct program, accelerating transition of their research to MITRE sponsors. Now in its 3rd year, the program has contributed to the development of 20 extraordinary individuals. Prior participants have had their work externally recognized, for example, as best papers at conferences, and even acquiring direct funding from the government. So, please lean forward and enjoy meeting one of MITRE's early career researchers.
I graduated from University of Michigan in 2011 with an undergraduate degree in electrical engineering with a focus in signal processing. I came to MITRE in July of that year, and I've been working in J82C, which is the signal processing department up here in Bedford. I'm currently pursuing a master's degree at Northeastern, also in electrical engineering. And in my spare time, I like to play guitar. I'll probably cut my hair before it gets that long, but no guarantees. Quick outline about what we're going to go through today. I'll give a pretty hearty background of the digital communication area, specifically wireless comms, and then we'll jump into the problem space and why traditional interference cancellation methods don't work well. And then we'll talk about the codated interference cancellation work that I did and wrap up with some results. In the most basic sense, communications is the transfer of information from a transmitter to a receiver. The transmitted signal is received at the receiver in the presence of noise, and it's transmitted through this channel, which we can model as H, which is just some multiplicative factor. An important tool in communications is what's called forward error correction, where we add some form of redundancy or parity to the information bits to make the transmitted sequence more robust towards the impairments of the channel and noise. So for example, here I just have a simple repetition code where each information bit, is just repeated 3 times, and we transmit that across the channel. We receive something, and we pump that into the decoder. So the decoding rule here would be something along the lines of, I look at every 3 bits, and I basically take a majority vote. If the majority of them indicate that a 0 was transmitted, then we'll decide a 0 for that information bit. And for more complex codes, this is a very basic code. For more complex codes, the decoding process can be iterative. So as we increase the number of iterations, the decode rate, which is to say the successful recovery of the transmitted information bits, increases. At the output of the decoder, in addition to these likelihood measures on the information bits, we can also get a likelihood measure on the coded bits, which would really be the bits that are actually transmitted across the channel. Now this is important because if we have a good estimate of what was transmitted at the beginning of the channel, and we have truth knowledge about what was received at the outside of the channel, we can do a better job of understanding what happened in between. So the model that I was focusing on, basic model like we spoke about earlier, doesn't take into account interference. So the wireless communication model does. It's very similar to the basic model in the sense that you're still transmitting information across a channel and you're receiving it in noise, but now that signal is also received in the presence of interference. And interference is kind of a catch-all. We use it to basically just model anything that isn't the desired signal. So oftentimes you don't know what the interference is, and so you lump it in with the noise term. Sometimes you do know what it is, and you can kind of estimate it and deal with it directly. So interference in modern wireless systems is inherent in the network design, thanks to high data rates, frequency reuse, everyone watching YouTube videos on their cell phone, things like that. And actually, the networks do a pretty decent job of actually handling a lot of those types of interference by themselves, by scheduling users to transmit at certain times on certain frequencies and things of this nature. But things get a lot worse when your interferers are a little bit dynamic and malicious in nature, and they have knowledge of your signal. Here you see on the bottom left, we have an LTE sort of resource grid without interference, and on the right, we have that same grid with interference. And the situation on the right is actually pretty diabolical because the interference is occurring on what's termed the reference symbols. And these are the symbols that the receiver uses to actually get the estimate of the channel and the noise and to receive to set up the decoding process. So if you're in the situation on the right and you're not actually performing any form of interference cancellation, you're going to really struggle to recover the information that was originally transmitted. So this is a quick little video. Hopefully it'll, sweet. If I haven't convinced you that interference is a problem, hopefully this will. You're going to see that the phone ringing actually results in keystrokes on the laptop, which if you're a user of the laptop is not something that you would want to happen.
2, 1, calling, engaging.
So it's starting to receive the signal now. We'll hear it ring. And the Word document parses it in some way or another. And so interference needs to be accounted for. Especially in this situation, rogue computers are never a good thing. So what can we do to account for the interference? Well, the space is well researched. There's a lot of traditional methods that have proven to be successful. Beamforming, which is a technique that projects your received signal into a more desirable subspace, whether you're trying to maximize SNR or minimize your error rate, things like that. Spatial nulling, you're actually trying to null out in space where your interference is coming from. If you have knowledge of the interference and the signal structure that it takes on, you can use serial or parallel interference cancellation, which actually looks to decode and then estimate the signal and then subtract out the interference. Decision feedback equalization is an iterative method where you're actually feeding back subsequent symbols, and that's a method that you want to use when your channel is especially bad. Now, what's the problem here? It's mostly that they make various assumptions about the environment that may or may not hold, and certainly don't hold for a long amount of time. So in things like beamforming and spatial nulling, ideally we have some spatial separation between your desired transmitter and the interference, but that isn't always the case. A lot of times you don't know what type of signal the interference is, whether it's someone just having fun at their house, just spewing RF, or if it's actually a neighboring LTE cell tower just transmitting broadcast information. And a lot of the interference in modern systems occurs in bursts, so running averages are going to give you inaccurate measurements, which in the end is going to degrade your code performance. So what we really want is a localized instantaneous estimate of the signal impairments, which brings us to the code-aided interference cancellation structure that I've been working on for the past year. So the idea here is that we modify the conventional receiver design to leverage the coded likelihoods available at the output of the decoder. So the top is your conventional receiver, where you basically just invert the transmitter and the channel, and ideally you get the information bits out. However, what we're going to do is we're going to add a feedback link that's going to take the coded likelihoods, which again are an estimate of what comes off your transmitter and into the channel. We're going to feed that information back, do some estimation, and ideally you incorporate those estimates into your forward receive chain, which is already well developed. The channel and the covariance estimates are typically the two things that are most important when you're trying to successfully receive the information in the wireless model. And what we can actually do is tie this back up into the traditional IC methods that I talked about earlier. So for instance, in this example, the first iteration we're going to run through the normal receive chain. On the output of the decoder, where we've got the coded likelihoods, we can do some estimation, get a better channel estimate, estimate the covariance of the noise a little bit better, and actually use that to drive a beamformer in this case. So on the second iteration, we're going to beamform, we're going to project the signal into a more desired subspace that using information that we didn't initially have. And then we're going to run the receiver again, and hopefully we decode, and if we don't, we can try it again, and if not, that probably means that you're just not going to get there and that you need to just request a retransmission of some sort. So let's skip the slide. So this all comes at a cost, of course. Running multiple iterations takes time. So we need to modify the conventional decoder algorithm to get these coded likelihoods at the output. A lot of the open source code typically just pumps out the information bits, but we need the coded likelihood. So that's a little bit of extra effort and time. We need to modify the conventional receiver structure, as you saw before, to incorporate these estimates and feed them back to the receive chain component. So a lot of those components now need to take in side information that they previously wouldn't have been designed to take in. And finally, we want a high throughput decoder to allow for the added iterations that are going to take up some time. So if we can decode a little bit faster, we can even things out time-wise if we're trying to implement a real-time system. So some initial results. A lot of this work coincides, well, almost all of it coincides with the work that I do for the Air Force using LTE. So integration has begun on the LTE downlink code base, where we've been iteratively refining the channel and covariance estimates for the broadcast channel. In LTE, the broadcast channel is a large source of interference because it's transmitting in the middle of the band periodically. And since in LTE all the cells are transmitting on the same frequency, you can imagine how this creates a lot of interference. And by virtue of running this architecture, we've had a 33% increase on real data that we collected on a test from a helicopter. So that was a great improvement, and what that does is it frees up. We can then pump that back into some form of interference cancellation, treat those signals as interference, and look for more cells that we can hopefully decode further down that are kind of lying in the weeds of the noise floor. And that analysis is ongoing for the Air Force. And then sometime this year, we're going to implement this structure into the HSPA Plus code base, which is a separate wireless standard than LTE, but at the end of the day, it's still using some form of error correction. And as long as we can get those coded likelihoods, which kind of serve as the foundation for this structure, then we'll be good to go. Signal structure has a large impact on performance. So the modulation schemes you use and the way that you set up that modulation scheme, whether it's gray coded, anti-gray coded, things like that, what type of code you're using. If your code has a lot of loops, which I won't say much about because it's very in-depth and technical and things of that nature, but the structure has an impact on performance, and so it doesn't work for every setup, and in others it does. The gains obviously depend on interference, but I'm working on this right now, and that's to apply a covariance estimation to transmit diversity reception. Transmit diversity is a multiple antenna technique that you typically see used in interference environments in place of MIMO techniques where you have independent streams. The TD reception algorithm typically assumes that your receive antennas are uncorrelated. And so in the plot here, we ran some quick simulations about what happens when your receive antennas are correlated. And you can see there's a significant performance loss along the lines of 6 dB. And so what we're trying to do is implement this, iteratively refine the covariance estimation, and hopefully pull that red curve back towards the blue curve as much as possible.